Today we're going to finish up talking about chemical reactions by discussing two other types of chemical reactions. This is going to be a double replacement reaction and a combustion reaction. So by the end of this video, you should be able to identify double replacement reactions and combustion reactions and use patterns to predict the products for double replacement reactions and combustion reactions. Okay, so first, what is a double replacement reaction? This is where two compounds, remember compound on these problems looks like two words put together, so where you have two compounds reacting to form two new compounds. The common form is going to be this: A and B plus C and D yield AD plus CB. If you've noticed, you just swapped the B and the D. So that's a double replacement. You have two things getting replaced now. You're just switching places between the B and the D here. Here's an example of a double replacement reaction. Copper sulfate plus beryllium oxalate yields what? Well, notice we've got two words plus two other words. So we've got a compound plus a compound. You don't have to use the activity series for these reactions. You just use the activity series for those single replacement reactions that we discussed in a previous video. But when you're doing double replacement reactions, you still need to know what's the metal and what's the non-metal, because remember, like replaces like. So in this case, copper is my metal and beryllium is a metal, so they're just going to swap places. So now I have copper oxalate plus beryllium sulfate, and you keep that Roman numeral with the attached with the copper. So copper and beryllium just switch places, and I've generated two new compounds here. Now, a neutralization reaction is a type of double replacement reaction, and a neutralization reaction is a reaction between an acid and a base. And in these reactions, the base is a metal hydroxide. So you got some metal with OH. The OH is the hydroxide. Here's an example of a neutralization reaction. Notice you still have two words plus two words, so it's a compound plus a compound. This will be my base because it's a metal with a hydroxide, and this is my acid right here. Acid's in the name. So just like we did previously with single replacement reactions, you're going to change the name of the acid back to hydrogen, and then it will end in ate. So nitric will change into nitrate. So this would be hydrogen nitrate. Then you can do the double reaction. The metal is going to replace the hydrogen. So I'm going to get aluminum nitrate. And you may wonder, well, wait, why water? Well, once you switch the aluminum with the hydrogen, over here you're going to have hydrogen hydroxide. But hydrogen hydroxide is the same thing as water. It's HOH, which is just H2O. So that's why we get water. So when you do a neutralization reaction, water is always going to be a product because you're always going to generate hydrogen hydroxide. Now let's talk about combustion reactions. Combustion reactions are reactions with oxygen. So you're going to have O2 as one of the reactants. And if one of your reactants contains C, carbon, then the product will be CO2, carbon dioxide. If one of the reactants contains H for hydrogen, then one of the products will be H2O, which is water. If one of the reactants is S for sulfur, then one of the products will be SO2. And if one of the reactants is N, then one of the products will be N2. So let's practice this. Say that I have CH4 plus O2. Automatically, I know this is a combustion reaction because one of my reactants is O2, oxygen. Anytime you are adding O2, as one of the reactants, it's going to be a combustion reaction. So now I look over at my other reactant, CH4. Because it has a C in it, I know one of my products is going to be CO2. And because there's an H over here, one of my products is going to be H2O. So just look back at the table to see where these came from. But if there's a C as a reactant, then I make CO2. And if there's an H as a reactant, then I make H2O. But you only do that when it's a combustion reaction. You only use that table when it's a combustion reaction. And we knew this one was because we're adding O2. All right, now we want to balance this. So I write C, H, and O because those are on both sides of the arrow. I have one C on the left, 4 H's on the left, and 2 O's on the left. I have one C on the right, 2 H's on the right, 3 O's on the right. You might wonder, where's the third O? So there's 2 right here plus this one right here. So now we can start balancing. I'm trying to get my H's balanced here. So I put a 2 right there. So that creates 4 H's for me. But it also makes it 4 O's now because that 2 multiplies the O as well, plus these 2 O's. So I'm going to put I'm going to try and get my O's balanced now. So I'm going to put a 2 right here. That will give me 4 O's. And now my C's, H's, and O's are balanced. I have 1 C on each side, 4 H's on each side, and 4 O's on each side. Helpful tip here, balance the O2 in these combustion reactions last. Do that last. All right, again, here's another example. I'm adding O2, so I know this is a combustion reaction. Since I have a reactant with an H in it, then I'm going to create H2O. And since this reactant has an N in it, I'm going to make N2. Again, just look back at the table for combustion reactions to see where these came from. Now, I have H's on each side, N's on each side, O's on each side. Now we write out how many to get it balanced. 3 H's on the left, 1 N on the left, 2 O's on the left, 2 H's on the right, 2 N's on the right, 1 O on the right. Okay, so let's get these H's balanced. So I put a 3 here because 3 and 2 will both go into 6. So now I have 6 H's on the right, but that 3 also multiplies the O. So now I have 3 O's on the right as well. 2 times this 3 H's will give me 6 H's, but the 2 also multiplies the N. So now I have 2 N's. So my H's are balanced, my N's are balanced, but my O's are not. I have 2 O's on the left. So what can I do? You can put the ideal decimal coefficient and then just double it. So the ideal would be 1.5. Now, why is that? Well, if you do 1.5 times 2, you'll get 3. And 3 would be balanced. But our coefficients can't have decimals in them. So what we do now is we just double all of the coefficients to get them to not be decimal, to not have a decimal anymore. So if I double 2, it becomes 4. If I double 1.5, it becomes 3. And if I double 3, it becomes 6. So since this was a 1 right here, there's an invisible 1. If I double that, it becomes 2. So those are the coefficients that we should write. We can't have coefficients that are decimals. But I just gave you a little tip to help you figure that out faster. And you can check yourself when you use these new coefficients, everything balances out. So to sum up, we've looked at double replacement reactions and combustion reactions, and you've learned how to predict the products for each type of reaction and balance those equations.